and therefore we cannot indefinitely increase the explanatory variables. And finally, we went for R bar square or adjusted R square. R bar square is an improvement over the standard definition of multiple R square. R bar square serves both the purposes. It, as the number of explanatory variable increases, ESS by TSS part that improves and that indicates, the explanatory power is increasing, but at the same time, it is checking the loss part in terms of degrees of freedom and making some kind of adjustment, and will be able to tell us whether we will incorporate one additional explanatory variable in our analysis or not. So later, in context of hypothesis testing analysis, once again we will come back to the idea of R bar square, and you will find that, when you are incorporating one explanatory variable, one new explanatory variable in your model, R square is always improving. However, R bar square may increase or even it may fall. Okay, because R bar square captures two issues. ESS is improving, that is one part, and another part is because of increment in number of parameters, degrees of freedom is falling. Okay, so it may happen that when you are increasing one explanatory variable, under certain context, R bar square may even fall. So it will give us indication when to incorporate a new explanatory variable in our model, or when we do not need to incorporate a particular explanatory variable in the model. It will tell us both the things. Okay, so it will give us a right judgment. So in context of hypothesis testing, once again, we will come back to this discussion of R bar square, etc. Before that, I'd like to complete discussion of two more R square, which I introduced last class, the simple R square and the partial R square. So let me first talk about the Pearson's product moment correlation, which is the simple correlation, and then we will talk about the partial correlation. All of you are aware about the definition of the Pearson's product moment correlation coefficient, the simple correlation. If you consider R square between any two variables x and y, it will give the definition covariance xi yi whole square divided by variance of xi into variance of yi. In this particular case, I have considered correlation, simple correlation between x and y. You can consider all x variables and the y variable together. You can consider a subset of x variables and y variable, or you may consider a subset of x variables, or you may consider the entire set of x variables when you are considering this simple correlation. So calculation of simple correlation is possible between one x and y, several x and y, all x and y. We can leave y. We can consider only the x variables, a subset of x variables you may consider, or you may consider the entire set of explanatory variables. So depending on the context, we will consider the simple correlation. Now, among all the correlations, all the simple correlations I am talking about, among them, the most important is simple correlation between all explanatory variables. That is the simple correlation between x1, x2 up to xk. So let me write the thing. This is the simple correlation between all explanatory variables. This is why this concept is important, or how this concept may help us in future tasks or decisions in a k-variable analysis. To understand this, let's consider the X matrix. Suppose I have up to k. Suppose this is our X matrix, okay? Now, if we consider the simple correlation between all x's, that means I'm considering the correlation between this set. Correlation between this set. Now, if I find this correlation is too high, in that case, there will be some problem related to determining the rank of the matrix. Okay. Now, while we discussed the assumption related to rank, we mentioned that the columns should be independent so that we can have full column rank. Now, if we get there is a high correlation between these columns, in that case, the columns will be linearly dependent on each other. And this rank condition, or the assumption of rank, that will not be satisfied, and you will be not able to estimate the parameters of the model. If the rank conditions are not satisfied, that means in future there will be some problem regarding the inversion part, x prime x inverse. So all these issues will come. If the columns are highly related to each other, there is linear relation among the columns. In that case, you will face a lot of problems related to assumption, related to estimation, etc. In fact, when the columns are linearly related to each other, this particular issue in the literature is known as problem of multicollinearity. So this multicollinearity problem will arise, and later we will find that there will be some problem related to estimation. In case of hypothesis testing exercise also, there will be some issues identified in presence of multicollinearity problem. Okay. So for detection of the multicollinearity, you may mention as a rule of thumb, you may first consider the correlation matrix. If the correlation is very high, if the simple correlation among the columns that is high, in that case you have to redo or rethink on your database. Okay, so this simple correlation in that way will help us to detect whether there is any multicollinearity issue in our data matrix or not. So multiple R square, which we discussed in the last class, that is the measure of goodness of fit. Multiple R square has some limitation, and therefore we shift to the notion of adjusted R square. Adjusted R square is a very good measure of goodness of fit. It can capture the idea that as we increase the number of explanatory variable, fit becomes better. At the same time, it can capture the idea as we increase the number of explanatory variable in the model, we are losing the degrees of freedom. Okay. Next, we are moving to the simple correlation. Simple correlation is Pearson's product moment correlation among several variables. Now, among all possibilities, the most useful one will be the correlation among all explanatory variables, because it can be used as a rule of thumb for detecting whether there is any multicollinearity issue or not. If there is multicollinearity, in that case, our estimation process will be suffered. So we have to rethink about the things, rethink about the database. Third, we are moving for partial correlation. The idea of partial correlation. Last day I mentioned, in case of partial correlation, we will consider the correlation between y and any of the x variables given rest of the x variables. So it is the correlation between y and one of the x variables given the rest. So if we write the this is this kind of concept. This partial R square is related to beta hat. Okay. Now, if I consider R square y x1 dot x2 to xk, so this beta hat is the beta hat which is coming with x1. So it is beta 1 hat. If I consider R square y x2 dot this will be associated with beta 2 hat and so on. So each of the partial correlation coefficient is associated with a particular regression coefficient. Regression coefficient associated with one explanatory variable. Now, if R square is associated with a regression coefficient, then it indicates given rest of the explanatory variables, what new will be explained by these particular explanatory variables. In other words, given x2 to xk, what will be the proportion which will be explained by x1 with respect to the variation in y. Variation in y is captured by TSS. Now, all these explanatory variables are trying to explain the variation in yi. That is the variation in, that is the TSS part. It tries to explain the proportion of TSS part. And together, the proportion of TSS, they can explain, we call the ESS, explained sum of squares. So each of the explanatory variable is trying its best to explain a proportion of TSS. So y x1 dot x2 to xk means given x2 to xk, what will be the proportion of variation in TSS will be explained by x1. So this R square is doing that job. It is telling us the proportion which will be explained by x1 with respect to the variation in yi given rest of the explanatory variables. So coming back to our analysis, partial correlation is the correlation between y and one of the explanatory variables, say xj, given the rest of the explanatory variables. that is partial correlation between explained variable y and any single explanatory variable, say xj, given all other x's, we are presenting by the notation rj square. Now, if we consider a null hypothesis, say beta j is equal to 0, under H naught, that is, if I consider this restriction is true, under H naught means if I consider this restriction is true, beta j is equal to 0, instead of RSS, we are getting RRSS, restricted RSS. In econometrics, if you put the null hypothesis in your original model, then your original model is called the unrestricted model, and the model under H naught is called the restricted model. So let me write the equations. Suppose this is the model to begin with. Then suppose we are considering a restriction or null hypothesis. So and this model is called the restricted model. Okay. The RSS of the first model is called the whereas RSS of the second model is called the RRSS. So this is the idea. If I consider a null hypothesis, in econometrics, null hypothesis is considered as a restriction. This is called a restriction. Okay. So if I put these in the model, we get a restricted model. So whenever there is a null hypothesis, actually we have two models, unrestricted original model and a new model, which is the restricted model. So we have two RSS. With respect to the first model, we have URSS. With respect to the second model, we have RRSS. Now anyone, please tell me whether URSS will be greater than RRSS or RRSS will be greater than URSS. The question is, or which one is true? Anyone? Restricted RSS is greater than unrestricted RSS, or unrestricted RSS is greater than restricted RSS? Or, there may be both the things. RRSS may be greater than URSS, or sometimes URSS may be greater than RRSS. What is your idea? Look at the models and tell me. Anyone? Aditya, what is the possibility? What do you think? What you are feeling? Just tell me that. Yes.
I think URSS is greater than RRSS.
URSS is greater than, you are telling that RSS of the unrestricted model will be greater than that of the restricted model. Am I right?
Yes, ma'am.
Why do you feel so?
And because there is an additional explanatory variable under URSS.
Okay, very good. If there is an additional explanatory variable in the first model, so why you are thinking that explanatory power of that model will be lesser?
And then the explanatory part will be greater if there is an additional explanatory variable.
Okay, so if you feel explanatory power of that model will be greater, so what about the RSS, residual part? You are telling me URSS will be greater than RRSS. This is your feeling. Then
Yes.
you are telling me if there is one additional explanatory variable, you feel that explanatory power of that model will be higher. So what about the RSS? Again, I am asking you. So Aditya?
Yes, ma'am.
So what do you want to change your proposition, or you want to stick to the proposition URSS will be greater than RRSS? Ujan? Yes, Ujan? What do you think? You got my question?
Yes. But
So what is your feeling? URSS, you will support Aditya? URSS greater than RRSS?
I'm not sure, ma'am.
Not sure. Anyone? Shubhangi?
Ma'am, in URSS, we can always choose what is or the coefficients that are in RRSS, but in RRSS, we can't, we are already not choosing one of the coefficients, we are restricting it. So I think URSS is, I am supporting it.
Okay. So now look at the thing. The second part identified, that is absolutely true. In the look at the first model. If you look at this model, okay, just look at this model. In this model, we have one more explanatory variable, x3i. So it is expected that explanatory capacity of this model will be bit higher than this one, where we have one less explanatory variables. This is the common notion, In the second model, we have less explanatory variable. In the first model, we have more explanatory variables. So it is expected that the first model will have less residual part compared to the second one. If ESS part is higher in the first one, unrestricted one, naturally RSS part will be lower compared to the second one. So in the second model, we will have greater residual component, lesser explanatory power, whereas in the first model, we will have greater explanatory power and lesser residual part. So in general, it is true that RRSS is greater than URSS. This part is true. The restricted RSS will be greater than URSS because in the restricted model, we have lesser explanatory variables. Now, if you look at the definition, TSS is equal to ESS plus RSS. Now, given TSS part, if ESS rises, RSS falls. In the first model, ESS is higher because there is more explanatory variable. So RSS will be lesser. In the second model, ESS is falling because we are reducing the number of explanatory variable. So RSS is increasing. So it is expected that in the restricted model, the residual component will be higher compared to the residual component of the unrestricted model. Okay. So in general, RRSS will be greater than URSS. Okay. What may happen if, the X2 has no explanatory, almost no explanatory capacity? This RRSS may be greater than equal to, this may be greater than equal to URSS. However, this is never possible. Unrestricted RSS cannot be greater than restricted RSS. Okay. In that case, the entire idea of regression model or ethics of regression will be questioned. We are increasing number of explanatory variable in the model to improve the position, which means more of the variation in yi will be explained if we incorporate more explanatory variables in the model. So in the beginning, we consider price as the only explanatory variable to discuss the demand, and then we explain if we incorporate income, if we incorporate taste and preference, gender, geographical location, etc., etc. In that case, you will be able to explain more variation in demand. Okay, demand can be explained in a better way if we incorporate all these explanatory components in the analysis. Okay, so never it is possible that URSS will be greater than RRSS because unrestricted model has greater explanatory power. So residual part, which is unexplained part, that will be lesser in the unrestricted model compared to the restricted model. Okay, so the relation between RRSS and URSS is finally RRSS greater than equal to URSS. This is the idea. Any question, any query, or are you understanding the things? Yes?
Ma'am,
Yes.
suppose the explanatory variable which we are choosing, suppose that it is a bad variable, that is, it is affecting in a negative way, then in that case, the restricted model is a
Negative means bad variable.
better
Negative means
unrestricted.
inverse relation. You are a PG student, so while you are asking some question, keep everything in your mind. Bad variable, why that will indicates negative relation. Negative relation means inverse relation between x and y. Negative relation does not mean it's a bad variable, isn't it? If taste and preference is negatively related with the demand, that means, there is an inverse relation. You may think this as inconsistent, because as taste and preference is improving, in that case, the demand is falling. So you may consider the thing in that way, but bad explanatory variable I didn't understand, and bad explanatory variable is negatively related. That also is not understandable. Okay, got?
Ma'am, I mean to say that uh,
The variable
if we are dropping
is
that
such
variable,
that it
better
doesn't
explanation.
have the explanatory power. Okay. So what may happen that you are considering the variable, however, when you are going for hypothesis testing, etc., you are finding it to be insignificant. This is one possibility. Or if you drop that variable, explanatory power of the model is not changing. In that case, your RRSS and URSS will be similar to each other, which I mentioned. Okay. However, this is impossible that a variable is insignificant. Yes, you are dropping the variable, and then you are finding that for the unrestricted model, RSS is higher. You know, do you think, is it possible? Who asked the question? I think Nauri. Okay, Nauri.
At most, it would be equal, right?
There is a possibility that RRSS can be greater than equal to URSS. However, RRSS cannot be less than URSS. The RSS of the restricted model, which has the lesser number of explanatory variables, cannot be less than a model which has greater number of explanatory variables. It may happen that x2 has no explanatory power at all, or x2 is insignificant. Okay. So in that case, if you drop the variable from the analysis, ESS will not differ between the models. Okay, suppose in the first model, x2 is not there. That is, you are getting the second model. So ESS will not increase because of inclusion of x2i. That may happen. Okay. In that case, the residual part of both the models will be equal to each other. So if bringing one additional explanatory variable, the explanatory power of the model does not improve. In that case, RSS of two models will be equal. However, it is not possible that while you are bringing a new variable in your analysis, explanatory power is falling and residual part is increasing. That is an impossibility. Okay. That is never possible. Explanatory power may remain constant. In general, it will improve. However, it may not improve if the variable is insignificant. Variable does not have any explanatory power. If the variable is irrelevant for the present discussion. So for all these cases, there will be no further improvement in ESS part if you incorporate that variable. So RSS of both restricted and unrestricted model will remain same. However, it is not possible while you are incorporating one irrelevant variable, or keeping one insignificant variable in your analysis, it is not possible that RSS of that model will be increasing or RSS will be higher. Got the point? Any other question? Is it okay, or do anyone else have any other question? So now, Aditya, you got the answer?
Yes, ma'am. Got it.
Okay.
Thank you.
So let's look at the propositions now. So consider a null hypothesis like this, beta j is equal to 0 under H naught. We get the RRSS. I hope now you are understanding what is the meaning of the RRSS. You are putting a restriction, you are dropping one explanatory variable. So you are putting a restriction, you are getting a new model. For the new model, you can calculate your RSS, and that RSS I am calling RRSS. When xj is additionally incorporated. So looking at the matter from the other way around, okay. So suppose in the first model, we do not have xj, we have the restriction there. And then xj is additionally incorporated. It will explain rj square portion of previously unexplained variation. So there is RRSS part. Now, if I incorporate a new explanatory variable xj, it will explain rj square portion of previously unexplained variation. Okay, so let's try to understand this point. So this has now we are incorporating x3i in the model, and this model is our URSS. This model is giving us the URSS. Okay, now what is the gap between URSS and RRSS? If I consider the partial correlation coefficient is given by, say, R3 square. In general, we have defined it as Rj square. So for third explanatory variable, the partial correlation coefficient can be considered as R3 square. Okay. So is it okay? Initially, in the first model, the restricted model, RSS is given by RRSS. Now I am incorporating one new explanatory variable. So Rj square portion of RRSS will be explained now. So in the new model, the RSS can be presented as RRSS, that is initial RSS, minus the portion which is coming to the explained part or the explanatory part or the ESS part, that is given by Rj square RRSS. So the new RSS is RRSS minus Rj square RRSS, and that will be equal to URSS. So Rj square is the portion of residual which has been explained by incorporation of a new explanatory variable x3i. So as we are bringing x3i, a portion of RRSS will be explained, and that portion is Rj square. So RRSS, that is the bigger RSS, minus Rj square RRSS, that is the portion of RRSS which is now explained, is giving us RSS of the new model. Is it accepted, or is there any question? Please ask me. So it is understandable to everyone?
That R squared J part, please explain once more.
Rj square is nothing but the partial correlation, the notation part, or what you want to know?
Ma'am, partial correlation, RJ square.
Rj square is the partial correlation,
Okay,
yes.
ma'am. Okay, ma'am.
Square is nothing but the partial correlation. It is equivalent to the partial correlation, it is R3 square in this particular case. And this is equal to actually R square y x3 dot x2. This is the thing. Okay, R square y x3 given x2. This is the Rj square or R3 square here. Now you got it?
Yes, ma'am.
So when xj is additionally incorporated, it will explain Rj square portion of previously unexplained variation. Unexplained variation means RSS. So 1 minus Rj square portion will still remain unexplained. So we can write URSS is equal to 1 minus Rj square RRSS. URSS is equal to 1 minus Rj square RRSS. And from there, we can proceed further. We can define the F statistic. F is equivalent to T square. T is the student's T. Okay. So we can define one F statistic which is equivalent to T square as RRSS minus URSS divided by URSS divided by degrees of freedom. Actually, from this idea, we can derive this kind of test statistic. We can define RRSS minus URSS divided by number of restrictions divided by URSS divided by degrees of freedom. This kind of test statistic can be defined in terms of RRSS, URSS, etc. Okay. So this idea is coming, we can frame this kind of statistic using the notion of RRSS, URSS, etc. Again, in context of hypothesis testing, I'll come back to this idea, how we can define F statistic, which is RRSS minus URSS. Always we will consider RRSS minus URSS because RRSS is greater than equal to URSS. Okay, URSS cannot be greater than RRSS. Okay. And in the denominator, we consider URSS, not RRSS, because with respect to the original one, we check the difference. RRSS we are getting when we are putting a restriction to the original model. So in the numerator, we are considering the difference between the two residuals. And this difference we are considering with respect to the residual of the original model. So in the denominator, we will consider URSS, not RRSS. However, this thing will come once again with respect to hypothesis testing. So for the time being, look at the thing. On the basis of the ideas which we have developed in context of partial correlation, we can define one F statistic which is equivalent to T square as RRSS minus 1 minus RJ square into RRSS. And these will be divided by number of restrictions. Here, the number of restrictions is equal to 1. So, I'm not considering divided by number of restrictions. However, the general formula, which we will discuss in context of hypothesis testing, that will be given by RRSS minus URSS divided by number of restrictions divided by URSS, or 1 minus RJ square into RRSS divided by degrees of freedom. Now for URSS, the degrees of freedom is given by n minus k. For RRSS, the degrees of freedom is different, because you are dropping one explanatory variable there. Okay. Now in our particular example, if I consider these particular example, in our restricted model, we have one explanatory variable, whereas in our unrestricted model, we have two explanatory variables. Can you tell me what will be the degrees of freedom of RRSS and what will be the degrees of freedom of URSS? Anyone? What will be the degrees of freedom here for RRSS?
N minus 2.
N minus 2, very good, because we have two parameters to estimate. So n minus 2, number of parameters in the model, that is 2, beta 1 and beta 2. So degrees of freedom is n minus 2. And what is the degrees of freedom of URSS?
N minus 3.
N minus 3. So what is the difference if I consider RRSS minus URSS? What will be the degrees of freedom for this difference? N minus 2 minus n plus 3 is equal to 1. Okay. So number of restrictions here, we are considering actually the difference of degrees of freedom of these two RSS, and here this is equal to 1. In our example, this is nothing but equal to 1. So, the number of restrictions, remember, that is nothing but the difference of degrees of freedom of RRSS and URSS. Okay, so for URSS, you are getting the entire degrees of freedom, n minus k. For RRSS, if you do not have, if you consider or if you drop one explanatory variable, it will be n minus within bracket k minus 1. However, for URSS, the degrees of freedom is given by n minus k. So it is written like this. And this is equivalent to F1, because in the numerator, you have 1 degree of freedom or 1 restriction only. So F1 comma n minus k. So this T square can be written as, n minus k. If I bring in, if I take RRSS common, so RRSS will drop from numerator and denominator. So it can be written as n minus k RJ square by 1 minus RJ square. Now, if you adjust this entire thing, you will find that RJ square is equal to TJ square by TJ square plus n minus k. So here it is t square is equal to n minus k rj square divided by 1 minus rj square. Now you can adjust the thing and you can find out the value of rj square, which will be given by tj square plus degrees of freedom. So there is a famous relationship between r square and t square, and which is given by r square is equal to t square by t square plus degrees of freedom. Remember, in case of a multiple regression, this r square is nothing but the partial r square. While we discuss this relationship for a two variable analysis, it doesn't matter whether we are talking about a simple correlation or partial correlation or multiple correlation, because all the concepts are identical in case of a two variable analysis. However, all the concepts are very, very different when we are moving to a multiple regression or we are increasing the number of explanatory variables in the model. So when we have more than one explanatory variables in our model, this kind of relationship, that is r square is equal to t square by t square plus degrees of freedom, can be established only in terms of partial r square, because t is related to the individual regression coefficient, and this partial r square is also related to the individual coefficient. So only t square can be related with the partial r square only. It cannot be related to multiple r square or r bar square or simple r square. Next, we will like to find out a relationship between simple r square, multiple r square, and partial r square. We want to establish a relationship between simple r square, multiple r square, and partial r square. To begin with, we are considering one model where the number of explanatory variables is given by 2. Suppose j is equal to 2. Number of explanatory variables we have in our model are given by 2 explanatory variables. Okay. So in that context, we can write the URSS or RSS of the original model in this format. URSS is equal to TSS minus TSS into multiple r square y dot 1 2. Okay, so let me first explain this. So we are starting with the relationship. Okay, so to begin with, we have the total model, So this RSS we can call the unrestricted RSS. ESS plus URSS. So okay. Now if I okay. So this is the idea. Now let me go back to my slide. So how I am writing the thing? RSS is equal to TSS minus TSS into R square. Okay. Okay, so there is a mistake in sign. Just a minute. So, okay, now we have two explanatory variables in the model. So I can write the thing as r square y dot 1, 2. We have two explanatory variables in the model, or the regression model is given by, say, so in this context, URSS is nothing but TSS into 1 minus r square y dot 1, 2. 1 and 2 indicates two explanatory variables, 1 and 2, x1 and x2. So it is written in this way. URSS is equal to TSS into 1 minus r square y dot 1, 2. Now I am putting a restriction beta 2 is equal to 0. Okay, we are putting a restriction beta 2 is equal to 0. Then the restricted regression has only one regressor x1, and we are getting RSS out of that, and that RSS is given by 1 minus r square y1 into TSS. Okay, so these two definitions are almost similar. In the earlier case, I wrote RSS is equal to TSS into 1 minus multiple r square. Now, when we have only one explanatory variable in the model, these multiple r square can be replaced by a simple r square, and we can write the relation as RRSS is equal to 1 minus the correlation between y and that explanatory variable. It's a simple correlation because we have only one explanatory variable in the model. So 1 minus r square y1 into TSS. Okay, so let me put the thing in the board again. So next, I'm considering a null hypothesis. So the new regression model is given by this is the new regression model. It's a two variable regression model. It's a simple model. We have only one explanatory variable here, and here we can write RSS, which is RRSS basically, is equal to TSS. Simple correlation between y and x1. So the two expressions are almost same. These two expressions are, similar kind of expression. Only because of the change in the nature of the regression model, we are getting some difference between the two. Conceptually, the two things are same. Okay, next. When additionally x2 is included, so I'm dropping x2 and then I'm telling that when additionally x2 is included, it explains r2 square. This is the partial correlation of the previously unexplained part and 1 minus R2 square part of it still remains unexplained. The way we explained in terms of Rj square. So when a new variable is there, a part of these RSS, and that part will be R square, will be explained. A part of RRSS will be explained, and that part will be R square of this one. That part will be explained, and 1 minus R square part of it still remains unexplained. So we can write, the right hand side as this is RRSS. So TSS into 1 minus R square Y1. A part of this is explained, that is R square Y2 dot 1. That part explained. So remaining part will be this one minus R square Y2 dot 1 part. So to explain this thing, So, the model becomes this one, looks like the unrestricted model, because x2i we are bringing to the above model. So we have a new explanatory variable x2i. So in that case, RSS of these model will become Is it okay? RSS of the new model, RRSS minus a portion of RRSS will be explained. So it will be RRSS minus R square Y x2 dot x1 RRSS. In other words, it will be, now RRSS is TSS into 1 minus R square Y1. Okay, and you can take RRSS common. So RRSS I am writing as okay. Now this model is equivalent to the original model, because in the original unrestricted model we had two explanatory variables x1i, x2i. So this RSS is basically nothing but RSS of the original model, URSS. This is equivalent to URSS because these two models, the green and the black one, has the similar structure. They are identical. In the red model, I dropped one explanatory variable. However, originally there were two explanatory variables x1i, x2i. And in the green version, when we are bringing x2i in the red model, we have the similar number of explanatory variables. So RSS of the green part and the black part are identical. So this is equal to the URSS part. Now URSS is equal to TSS into next. URSS is equal to TSS into 1 minus R square Y dot 1 2. So TSS and this is TSS into 1 minus R square Y x2 dot x1 into 1 minus R square y1. So we will cancel TSS from both the sides and we are getting the relation So this is the relation between multiple R square, simple R square and partial R square. Capital R square y dot 1 2 is the multiple R square. R square y x2 dot x1 is the partial R square. R square y1, that is the simple R square. So this is the relationship between multiple R square, partial R square and simple R square. So if you look at the PDF version, we did the same thing, and finally we got this kind of relationship. 1 minus capital R square y dot 1 2 is equal to 1 minus R square y1 into 1 minus R square y2 dot 1. And this relationship can be generalized for j is equal to k greater than 2. So this we have constructed for the simplest case, considering only 2 explanatory variables, and when we are putting the restriction, it is becoming the simple model. However, this can be generalized. Tell me if you have any query, any question for any part. The relationship between multiple R square, simple R square and partial R square. Anyone, any question? Is it okay? Rudra, any question?
No, ma'am.
ম্যাম একবার পেনটা একবার
Yeah. Yes, Orkodeep?
থ্যাংক ইউ ম্যাম
Okay. So this completes the discussion on 3 types of R squared. Actually, all these things, or most of the things will come back repetitively in context of hypothesis testing and then in case of regression diagnostics, okay? However, you need to understand the basics before moving towards all these concepts. So next, we will talk about some distributional aspects. Actually, we are moving towards the hypothesis testing. So we need to bring the idea of distributions, etc. So in case of a multiple regression, UI, this is following the multi-level normal distribution. Okay, so it is multinomial normal, multi-level normal distribution with mean 0 or expectation of UI is equal to 0 and variance covariance of UI is given by sigma u square in. By this time, you are familiar with this notation, sigma u square in, which is giving us the spherical variance covariance matrix for the error term. All the diagonal elements are constant, given by sigma u square, which is indicating homoscedasticity. All the off-diagonal terms are equal to 0. So you can take sigma u square common. So you are getting sigma u square multiplied with the identity matrix. So we are getting a spherical variance covariance matrix or spherical dispersion matrix here for the error term. Here beta hat is the set of best linear unbiased estimators satisfying the following condition. Beta hat is also following the multi-level normal distribution with expectation of beta hat is equal to beta. So in the previous class, we did all these things. Expectation of beta hat vector is equal to beta vector. And we derived the variance covariance matrix for beta hat vector that is given by sigma u square x prime x inverse. So it is following the multi-level normal distribution with expectation beta and the variance covariance matrix sigma u square x prime x inverse. Now, as you know, under most of the circumstances, sigma u square will remain unknown. So we will use the unbiased estimator for sigma u square given by SU square equal to RSS by n minus k. So expectation of SU square is equal to sigma u square. Already we did all these parts, derivation of sigma u square or the estimator of sigma u square, etc. So we don't need to repeat this thing. Only we will discuss the distributional aspects. Now, expectation of SU square is equal to sigma u square, and we can consider the ratio of variances like SU square by sigma u square. We can consider the ratio of variances SU square by sigma u square, and if I multiply this with n minus k, that is following a chi-square distribution with degrees of freedom n minus k. Now, from your undergraduate level, you have idea about the inference where you considered the ratio of sample variance to the population variance. Now, ratio of sample variance to the population variance, if it is multiplied with the relevant degrees of freedom, in that case, it follows chi-square with n minus k degrees of freedom. Chi-square with the relevant degrees of freedom. Okay. So here, when you are considering the ratio SU square by sigma u square, and you are multiplying it with the relevant degrees of freedom n minus k, that will follow chi-square distribution with degrees of freedom n minus k. Actually, chi-square is the sum of squares of standard normal deviates. So if you look at the thing, if you consider n minus k into SU square, basically you are getting RSS. So this ratio is giving you RSS by sigma u square. Okay, so it is residual sum of squares by sigma u square. We are considering n minus k SU square by sigma u square, and SU square is RSS by n minus k. So n minus k SU square so this is okay, RSS by sigma u square. Now, chi-square is the sum of squares of standard normal deviates. Now, when we are considering residual sum of squares, you are getting sum of squares by the very definition of residual sum of squares, and all of the residuals will be normalized when you are considering or dividing it by sigma u square. Okay, all of the residuals will be standardized if you divide it by sigma u square. So this will give you sum of squares of standard normal deviates, sum of squares of standard normal deviates, and therefore it will follow the chi-square distribution with n minus k degrees of freedom. Okay, so you are getting sum of squares of the standard normal deviates when you are considering the ratio of variances, ratio of sample variance to the population variance multiplied with the relevant degrees of freedom. So following that logic of inference, here we are putting the distribution of these n minus k su square by sigma u square or RSS by sigma u square. Coming to the interval estimation part first, for a single unknown parameter beta, we know that beta hat minus beta divided by standard error of beta hat, this follows t distribution, student's t distribution, because it is beta hat minus expectation of beta hat divided by standard error of beta hat. In the standard error of beta hat formula, we use sigma u square divided by summation xi square. Now, when sigma u square is not known, we have to replace it by su square. And if I replace it by su square, in that case, no more it will follow the tau distribution, rather it will follow the t distribution with relevant degrees of freedom. So we are thinking that, or we are assuming that, we are considering that sigma square is unknown, and therefore we are considering the t distribution rather than tau distribution. So for a single unknown parameter beta, we know that beta hat minus expectation of beta hat divided by standard error of beta hat will follow t alpha n minus k, where alpha is the level of significance, and we assume that sigma square is unknown. Remember, if somehow you have some knowledge about sigma square, it will be tau rather than t, tau rather than t. So the 95% confidence interval is given by probability minus t, here there will be alpha by 2. Okay, there is a mistake. It will be alpha by 2 minus t alpha by 2 n minus k less than beta hat minus beta divided by standard error of beta less than t alpha by 2 n minus k. So I'm requesting everybody to note down the proposition, please add alpha by 2 instead of alpha. It will be alpha by 2 is equal to 0.95. So the confidence limits are beta hat plus minus standard error of beta hat t alpha by 2 n minus k. So this will be the confidence interval for beta confidence interval for beta. So the only thing you have to remember somehow, if you have knowledge about sigma square, you have to write the interval in terms of tau. The rest of the things will be identical. However, under most of the circumstances, you will have no knowledge about sigma square. So the standard practice of writing the interval for beta hat is given by this. Now, in context of a multiple regression, the entire proposition will remain unchanged. Only in place of standard error of beta hat, instead of considering sigma square divided by summation xi square, we will consider these variance covariance metrics. Okay. In case of a multiple regression, the entire proposition is same. Instead of a single beta in place of expectation, we get a vector. And instead of getting a single element, sigma u square divided by summation xi square, here we get a matrix, sigma u square x prime x inverse. So there will be no change in the proposition if we consider a multiple regression case. In that case, simultaneously for the entire beta vector, you are finding the range. For the entire beta vector, the range is given by beta hat vector plus minus the standard error beta hat means the square root of the variance covariance matrix, the square root of the variance covariance matrix. That is, we are considering square root of this entire matrix sigma u square x prime x inverse into t alpha by 2 n minus k. So the entire proposition will remain unchanged, only a single element will be replaced by vector, and here the standard error will be replaced by the entire standard error matrix of beta hat. The interval for sigma square can be presented as follows: probability chi square n minus k 1 minus alpha by 2 less than n minus k u square by sigma u square less than chi square n minus k alpha by 2 is equal to 0.95. And finally, you can do these things. A lot of things are there. You have to reverse this, so you will get 1 upon 1 upon 1 upon here, and then if you reverse the entire thing, actually this part will go to the left, this part will go to the right. If you want to maintain the sequence, that is the left hand side is less than sigma square, less than this. Okay, so you have, all of you have idea about all these things, how to consider the upper and lower limit for sigma u square. So complete all the steps in between. I have written the first step and the last step, and it is your task is to complete all the steps in between, so that clearly you understand you are getting this component as the lower limit and this component as the upper limit. And remember, chi-square is not a symmetric distribution, and therefore at the left tail you have to maintain 1 minus alpha by 2, and in the right tail you have to maintain alpha by 2. So t is a symmetric thing, so I consider minus t alpha by 2 and plus t alpha by 2, whereas in case of chi-square, since it is a positively skewed distribution, you have to maintain with 1 minus alpha by 2 and alpha by 2. Any question regarding the interval estimation? Hope by this time everyone changed this alpha to alpha by 2 for the t, alpha by 2. All this alpha will be alpha by 2. Anyone, any question regarding the statistic we are using, the way we are presenting the interval for the regression coefficient and for sigma u square? Because these are the two things, which we bother when we consider the estimation part. So in the interval estimation, we are thinking about the entire beta vector, which are unknown, and the sigma u square, which is also unknown in the regression analysis. Do anyone have any question? So everybody is understanding everything? So next we will move for hypothesis testing. So this is the k variable regression model. Yi is equal to beta 1 plus beta 2 x2i plus beta k xki plus ui for all I is equal to 1 to 2n. Three types of hypothesis possible in context of a multiple regression. The first variety is consider a single coefficient and check whether it is significant or not. Just like a two variable case. In two variable case, we considered the regression coefficient and constructed the hypothesis h naught colon beta 1 is equal to 0. So that kind of hypothesis. So in a multiple regression, the similar thing can be done for all parameters in the model. So it can be started with beta 1, beta 2, beta 3, beta k. We can do it for each and every regression coefficient. So one possibility is consider one explanatory variable and check what is the associated regression coefficient with it. Check whether this coefficient is significant or not. Put the null hypothesis beta j is equal to 0. Okay, and this will test whether this explanatory variable has an important causal relation with y or not. If the hypothesis is accepted, in that case there is no relation. If the hypothesis is rejected, in that case there is a relation between y and these particular xi or xj. Okay, so this is one type. This is the first variety. The second variety is you can run a test to check whether overall the model is significant or not. Whether overall the model is significant or not. So to do this, we are considering all coefficients present in the model. Beta 1 is equal to beta 2 is equal to beta 3 is equal to up to beta k is equal to 0. So we are considering all the coefficients present in the model and setting this to be equal to 0. So if this null hypothesis is accepted, in that case, the proposed regression equation is meaningless. Overall, the explanatory variables cannot explain yi. Okay, the explanatory variables together cannot explain yi. So the proposed regression equation is not meaningful. And if we reject the thing, overall the model is significant. Finally, we can consider a subset of the regressors, that is, we can consider two regression coefficients, say beta 1 and beta 2. We can establish a relationship between them, beta 1 plus beta 2, and we may check whether beta 1 plus beta 2 is equal to 0 or not. Okay, or you may check beta 1 minus beta 2 is equal to 0 or not, or you may check beta 1 plus beta 2 plus beta 3 is equal to 0 or not. Okay, so this kind of proposition, you are taking a subset, or you are considering a relationship between the explanatory variables and checking whether this relationship is significant or not. So that is another variety. Today I'll talk about 1 and 2, and next day I'll talk about the third variety. Tomorrow I'll talk about the third one. The first one, you are very, very familiar with this at your undergraduate level. All of you did this thing. So hypothesis test for a single coefficient. Hypothesis is beta j is equal to 0. Now we consider the statistic beta hat minus expectation of beta hat divided by standard error of beta hat. To test beta j is equal to 0, we consider the statistic okay, this kind of thing. Now under the, this is equivalent to, since it is the unbiased estimator, beta hat j is the unbiased estimator of beta j. So expectation of beta hat j is equal to beta j divided by standard error of beta hat j. So which is this kind of thing. Under the null hypothesis, because under H naught, beta j is equal to 0, so we can write the statistic as beta hat divided by standard error of beta hat. Now, as long as in the standard error definition, I am writing sigma u square, which means we have knowledge about sigma u square, this will be equivalent to tau. As long as we have knowledge about this sigma u square, we know this sigma u square, this will be given by tau. However, if I write the definition as beta hat j divided by SU square, sorry, That is, I replace sigma u square by su square, where su square is equal to RSS by degrees of freedom. This statistic will change to t distribution. So as long as I have knowledge about sigma u square, we will use tau. However, if we do not have knowledge about sigma u square, the entire proposition will remain same. However, in the denominator, sigma u square will be replaced by su square. And as I do so, you know, we are getting basically tau divided by chi square deflated by degrees of freedom. And that will be equivalent to t distribution. So here either a tau distribution or t distribution will be used to test the proposition, depending on the situation, whether you have knowledge about sigma u square or you have no knowledge about sigma u square. And the steps are given: beta hat j minus expectation divided by standard error. Expectation of beta hat j is equal to beta j, as beta hat j is an unbiased estimator of beta j. And under the null hypothesis, this beta j is equal to 0. So we get the idea beta hat j divided by standard error of beta hat j. So coming back to this tau naught, tau under the null hypothesis, tau naught is equal to beta hat divided by sigma u square divided by summation xi square. This is following the standard normal distribution, okay? And expectation of beta hat j is equal to beta j is equal to 0 under h naught. And again, we are putting the thing, you know, n minus k su square by sigma u square is equal to RSS by sigma u square. Already we checked this is following the chi-square distribution with n minus k degrees of freedom. So if I have no knowledge about sigma u square, we have to combine the earlier tau and this knowledge, that is n minus k su square by sigma u square, will follow chi-square distribution to frame a t statistic, which is given as tau naught. This entire thing will be there. And in the denominator, we will put n minus k su square by sigma u square for making an adjustment, okay? So that we are getting tau divided by root over chi square divided by degrees of freedom. And finally, this can be presented as, you know, beta hat by su root over summation xi square, or root over su square by summation xi square. So beta hat divided by standard error of beta hat, which is following the t distribution. So the things have been done following all the steps, you know. So some basic idea we are getting from this presentation, and actually the things are taking place in this way. We can start with tau and then we can bring chi-square. Tau and chi-square together is framing t. So, you know, the standard statistic which generally we use, that is the beta hat divided by standard error of beta hat, and that is given by t distribution as discussed in this presentation. Now, this null hypothesis can be tested against the alternative specification t, you know, beta j greater than 0, beta j less than 0, beta j not equal to 0. So for the first two varieties, that is beta j greater than 0 and beta j less than 0, we are considering the one tilt test. So we will keep alpha in the statistic when we will consider the thing. And if we consider the not equal to 0, that is if we consider the two tail test, in that case the rejection area will be evenly distributed at two tails of the distribution. So we have to consider alpha by 2, t alpha by 2 n minus k. So if the estimated t is greater than t alpha n minus k, then h naught will be rejected at alpha percent level of significance. However, these proposition, that is t greater than t alpha n minus k, will change depending on whether you are considering the one tail test or you are considering a two-tailed test. Okay, so in the note it has been added, the level of significance will be determined by alternative hypothesis. Okay, so as you do, in case of any hypothesis testing, we do the things in this way. Any question regarding the first variety when you are testing for a single coefficient? If anyone have any question regarding the formation of the test statistic, regarding, level of significance or whatever you want to know. Anyone, any question? Titir, are you understanding the matter?
Yes, ma'am, got it.
And the second variety, as I mentioned, considering all coefficients to be equal to 0, testing for significance of the entire model. So beta 2 is equal to beta 3 is equal to up to beta k is equal to 0. This test is done by the F statistic. So you are familiar with this F, today I discussed about this F. F can be presented as RRSS minus URSS divided by number of restrictions divided by URSS divided by degrees of freedom. And if the number of restriction is given by small r, in that case it will follow F with degrees of freedom r comma n minus k. In that case, we considered a single restriction. So it was F1 n minus k. However, in general, here we are considering, say, k minus 1 number of restrictions. So R will be k minus 1. So it depends on how many restrictions you are putting. And this number of restrictions is nothing but the differences of degrees of freedom of RRSS and URSS. So while you will check these notes, please write down the degrees of freedom of RRSS, degrees of freedom of URSS. Degrees of freedom of URSS is already given in minus k. However, please write down the degrees of freedom of RRSS and check whether the number of restriction is exactly equal to the difference between degrees of freedom between RRSS and URSS. Now under H0, if I consider all explanatory variables have no power to explain yi, that is starting from beta 2 to beta k is equal to 0, under H0, we are proposing that ESS is absolutely equal to 0. No explanatory power. ESS is equal to 0. Hence, for the restricted model, RRSS is equivalent to TSS. In general, by ANOVA, TSS is equal to ESS plus RSS. If I find under restriction ESS is equal to 0, in that case TSS is equal to RSS. Now RSS of the restricted model is called the RRSS. So under the restriction or under H0, when ESS is equal to 0, we get RRSS is equivalent to TSS. For the unrestricted model, we are considering URSS to be equivalent to simply RSS. For the unrestricted model, the RSS is called the URSS. Here, for the original model, URSS we are calling the RSS, or we are understanding this is equivalent to RSS. And hence, the F statistic can be reframed as or redefined as RRSS I replaced by TSS. So F is equal to TSS minus URSS I changed by RSS. So TSS minus RSS, total number of restriction we are considering K, all K restrictions we are considering, divided by URSS we are calling RSS. So RSS by N minus K. Now TSS minus RSS is nothing but ESS. So ESS by K by RSS by N minus K, deflating both numerator and denominator by TSS. So in the numerator, we are getting R squared, while in the denominator, we are getting 1 minus R squared. So it is R squared by degrees of R squared by number of restrictions divided by 1 minus R squared divided by degrees of freedom. So for a multiple regression, if you have knowledge only about R square, or somehow if you are able to calculate R square, in that case, you will be able to frame your F statistic. So if you have information on restricted RSS, unrestricted RSS, you have to go by this formula. However, if you do not have information on this thing, however, if you have information on R square, then also you will be able to calculate F. You will be able to calculate F. So if you have information on measure of goodness of fit, you can frame F statistic to check overall whether the model has significance or not. You are doing a number of practical sessions, I think in Excel especially. You did something on regression, and you will get in one table, you are getting information on R square, R bar square, F, etc. All these things are given in a particular table, before the coefficient table, just because of the fact that all these things, R square, R bar square, EF, these give you some idea about overall significance of the model. So F can be calculated or estimated on the basis of multiple R square only. Okay. So if you are familiar with the regression output in Excel only, I'm not talking about R, or I'm not talking about Stata. If you are familiar with the regression output in Excel only, you have some idea that all these things come in a particular table, and this table is giving you the idea about goodness of fit as well as overall significance of the model. So for today, this is all. Tomorrow we will continue from this point. Any question on this particular frame? Any question, any doubt, or any problem?